Hey YouTube, Kinetic Mind 89 here. My real name is David. I'm a double major, physics and applied discrete math. I'm about to start a series of videos on teaching simple physics concepts, or not so simple, but I'm going to attempt to make them simple. I want to try to help you guys learn things in a more simple, compact way, and also explain them in a simple way so I can understand them better. This first video is going to be about the magnetic field and magnetic forces. But before I start talking about that, I want to share a quote with you guys from Einstein that relates to how I'm going to try to or attempt to teach a lot of these concepts in these videos. And the quote is this: if you can't explain it to a 6-year-old, you don't understand it yourself. Einstein. So there you go. He said that, so what else do we need? But yeah, what I'm talking about today, as I said, is the magnetic field. And we really have magnetic fields or we deal with magnets and magnetic fields in so many of our appliances. There's so many practical applications. The MRI, the Large Hadron Collider, uses magnetic fields to hold subatomic particles in place. Electric motors uses electromagnetism, which involves magnetism. Even those cool pictures you hang on your refrigerator that has magnets, so that's cool. Magnets are involved there. They're very fundamental in our society, magnetism and magnets. And just getting past the practical side, there are a few fundamental concepts that must be understood about magnetism before we can actually start working physics problems. Now, these concepts might take a while to sink in. I'm going to read them out of my book, and it took me some time to actually think about these, actually fully grasp them. So I'm going to read them kind of slowly, and you guys watching can just soak these in. These will really help you do the actual problems once you understand the concepts. If you don't understand the concepts, you don't really know what you're messing with. Sometimes the algebra can get confusing. So it's really good to know the concepts in physics. That is a good start, is to have your fundamentals with the concepts down. The first is the magnetic force, Fb, which is denoted Fb, the magnetic force, is proportional to charge Q of the particle as well as speed v of the particle. So the word proportional in physics just means if one goes up, the other goes up. If one goes down, the other goes down. So the magnetic force goes up with charge, and it goes up with velocity. The magnetic force goes down with charge, and it goes down with velocity. When a charged particle moves parallel to the magnetic field vector, the charge is zero. Or I'm sorry, the magnetic force on the charge is zero. Because if it's going parallel, it's going with the field, and it can't actually create a force if it's going with the field. It would have to go against it. And the opposite is true if it's perpendicular to the field. If it's perpendicular, the force is going to be at a maximum because it's going to be going straight through this field at a 90-degree angle, and that field is going to push it at its maximum, so the force is going to be maximum. We'll talk a little bit more about that later. The magnetic force on negative charge is directed opposite of that force on a positive charge, moving in the same direction. So the force would be, if you have a proton heading through this field this way, you might have a force acting up, but if you have an electron heading the same way through this field, it's going to be pushed down. The force is going to push down, because that is just a fundamental principle. I can't tell you why for that exactly. But going into a little bit more of the math, I'll start writing the formulas for you guys. I'll erase this great Einstein quote, or great to me anyways. The first formula is, and this is kind of what I talked about, the force, magnetic force, is equal to charge times the velocity of the particle times, and this is actually a cross product. I said times, but this is a cross product, and we'll talk a little bit more about that. So both of these are vectors. And a vector just means it has a magnitude and a direction. So it has a given number to it and a direction. So our force for a magnetic field acting on a particle is the charge of the particle. This Q is the charge of the particle. But this is fundamental too, to actually know what these variables mean. So again, just to be really explicit here and say this over again, over and over again, this is the force of the magnetic field on a given particle, FB. Q is the charge of the particle, which the charge of a proton and an electron is exactly the same. Proton's positive, electron's negative, just in, obviously one's positive, one's negative. This is the velocity. Again, it has a direction and a magnitude. The units is meters per second. This here is the magnetic field, and it has, its direction is the direction that the compass points north. And, or the compass needle points north. That's the actual direction of the magnetic field. And its units is Tesla. So in dealing with that, we've identified our variables. And sometimes we'll not actually ask for the vector quantity of the force. This is asking us for a direction and a magnitude. Sometimes we're just asked for the magnitude. And that's actually a bit more simple, and I haven't memorized it yet. You probably see me looking down. I'm looking at my notes here. That is actually, if I can get my markers to work, that's actually the absolute value of Q times V and then B sine theta. Okay, so this here, this is just the magnitude. We're not looking for direction here. All we're looking for is how much force is this magnetic field exerting. And with that being said, what we need is, we just need the constant of a charged particle, which is given in your physics book. If you're in physics, just look this up, you'll find it. This times V, which is the velocity, times B, which is the magnetic force. It'll be in Teslas, but you don't need a direction, you just need a number. And you multiply it times sine theta. And theta is the angle that is made between the actual cross product. And we'll talk a little bit more about that in a second. And I was going to share with you some rules for unit vectors, but I don't think I'm going to have enough time in a 15-minute video. I know that's YouTube's cap. So I'm going to go straight into talking about the right-hand rule here. And what I've set up over on this wall is, you can see this tape. You probably can't see what's actually written on the tape. This top one here is the force, the magnetic force. This one here is the velocity, and this one here is the magnetic field. And this is to illustrate the right-hand rule in 3 dimensions, because in books, in physics books, it's usually represented in 2 dimensions. That's difficult. Now what they teach you is, and I'll try to let you see this and still see my hand, see if that's possible. What they teach you is this here will be, and I'll use a ruler to illustrate, this here will be your y-axis. Your knuckles here, the direction they run, this will be your x-axis. And your knuckles in this direction, this will be your z-axis. And what we can know by this is, whichever direction of any of these 2 variables are in, the other one is going to be respective to the position, as labeled here. For instance, if you have V is going west, and you have the velocity is going west, you have a particle like going west, traveling west at a given velocity, and the force on that particle is upward or north, whichever you define that as, depending on your your coordinate system or your what you're relating it to. If you know those 2 things, then you know B is going to be outward or in this direction, which would be behind you. If I was facing the wall and the velocity was west and the force was upward, I guess you could define this as north. Or I'm sorry, I guess you could define B as south. You could say that B was south. And that is very important to know in determining the actual direction of the force. Because another fundamental thing, the force of a magnetic field cannot change the velocity of a particle. It can change the direction, but not the velocity. That would not agree with the work energy theorem. And I'm going to get into solving. Hopefully I'll have enough time on this one video to finish one problem. If not, I'm going to make another video right after this, and I'm going to read this question to you. Let me find it here really quickly. I lost my placeholder. Here it is. I'm going to read the question, and then what I'm going to do is just list all appropriate variables, and instead of writing the entire question out, I'll just write the pertinent information. And that's another thing in physics, more so than knowing knowledge and knowing facts like other fields of study. It's more so about problem solving and your skills with problem solving and developing a methodology to solving your problem. So that's one. I'm going to share with you my methodology to solving problems, but I'm not saying it's necessarily the best. I'm saying it works for me. Everybody has their own methodologies, but what works for me is actually I'll write all of the variables that I do know, and then I'll write the variable I don't know. I'll write the variable that they're looking for, and I'll think, well, boom, 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 I got these variables. What equation can I use? And I'll find an equation. Sometimes it's more than one. Sometimes it takes multiple equations to solve for the variable I need, the unknown variable. So I'm going to start by reading this question to you guys. And actually, you know what? I'm going to end this video. Tune in for part 2 of the same video, because I can already tell I'm not going to have enough time to finish this. I don't want to split one problem into 2 videos. That would be confusing. So I will talk to you guys in a second. Peace.